Mathematical optimization is incredibly powerful. You can feed an algorithm your resources and goals, and it will hand you a perfectly mapped out strategy. But that precision relies on a massive, hidden assumption that the real world will stay exactly the same. Take a business like Blue Ridge Hot Tubs, run by an owner named Howie Jones. Howie manufactures two main products to drive his revenue: the premium Aqua Spa and the standard Hydrolux. This formulation shows the strict constraints Howie operates under for the upcoming month. He has exactly 200 pumps, 1,566 labor hours, and 2,880 feet of tubing available. Every tub he builds eats into those specific caps. By plugging those limits into a standard linear programming model, Howie gets a mathematically perfect answer. To make the most money possible, he should build exactly 122 Aqua Spas and 78 Hydroluxes. Not one more, not one less. But then, Monday morning hits. A supplier raises the price, a rival cuts retail prices, or workers call in sick. The rigid conditions of the model are gone. If reality shifts by even 1%, you might wonder if the whole original plan has to be scrapped. That is where a technique called sensitivity analysis comes in. It allows you to stress test your mathematical model against real-world chaos without having to calculate everything from scratch. Let's say a competitor suddenly drops their prices, and Howie is forced to reduce the retail price of his Aqua Spa just to stay competitive. Because his profit per unit has changed, it seems like his entire manufacturing schedule is now wrong. But Howie doesn't need to rebuild his strategy, thanks to a concept known as the allowable range. This table shows the exact boundaries. Under variable cells, the allowable increase and decrease for the Aqua Spa are 150. Since the original profit was $350, fluctuating between $300 and $450 guarantees building 122 Aqua Spas is still his best move. The actual amount of cash he deposits in the bank at the end of the month will drop because of the lower price, but the strategy, how he deploys his parts and his people on the factory floor, remains entirely intact. Now imagine a different crisis. Production is humming along, Howie has plenty of unused tubing and pumps sitting on the shelves, but he has burned through his maximum limit of 1,566 labor hours. He has to make an immediate high-stakes operational decision. Should he pay his workers premium overtime rates to keep the assembly line moving? To answer that, we look to a metric called the shadow price. This represents the exact hidden dollar value of adding just one single unit of a tapped-out resource to your factory. This constraints report gives us that exact number. Look at row 9, the labor constraint. The table reveals that the shadow price for one additional hour of work is exactly $55.55. That number is a hard ceiling. It tells Howie that paying a worker $40 an hour for overtime will increase his overall profits, but paying them $60 an hour will actively cannibalize his margins. The math makes the decision for him. But what happens when the model looks at your inventory and decides one of your products isn't even worth manufacturing at all? This table illustrates how the algorithm evaluates an underperforming product through a metric called reduced cost. It calculates the total value of the raw materials and labor a product consumes, in this case $333.33 for product 2, and compares it against the profit it brings in. When a product costs more in shadow resources than it generates in revenue, its production target becomes 0. If Howie ignores the model and insists on building just one unit of this unprofitable item, his total factory profit will drop by the exact amount of that reduced cost. That reduced cost figure gives you a clear operational target. It tells you precisely how much your raw materials or labor need to drop in price before that specific product becomes worth manufacturing again. There is, however, a breaking point in this system known as degeneracy. You'll spot it in a sensitivity report when the allowable increase or decrease on a constraint reads as exactly 0. A 0 means you have hit total mathematical gridlock. At this point, the standard rules of prediction fail. Adjusting a resource by even a fraction of a unit might completely upend your strategy, indicating that alternate optimal solutions might exist. If you scale this up from a single hot tub factory to global shipping networks or international supply chains, the stakes of these calculations become astronomical. Linear programming is rarely a matter of calculating a single, static answer and blindly following it for months on end. Instead, it acts as a dynamic radar map, constantly pinging the shifting conditions of your business. When supply lines break, prices fluctuate, and competitors react, the most valuable insight isn't knowing the perfect move for right now. It is knowing exactly how far your reality can bend before your entire strategy breaks.